Hello again for the second part of our application layer security topic. I will talk about two protocols, SMTP and DNS, and we will talk about their security and what kind of attacks can be performed to these protocols. So let's start with SMTP. So this is a protocol for mail transfer. So SMTP is short for Simple Mail Transfer Protocol. So in this scenario we have user agents that use mail clients like Outlook Express or something, and we have mail servers where our mailbox is actually stored and the messages are queued at the servers. So this is for the final version. You can check RFC 2821. So SMTP is the main application layer protocol for internet email. It is much older than HTTP. The first RFC appeared in 1982. I wasn't even born in that year, so it is really old. So it uses TCP to transfer email message from client to server on port 25, but note that this port for 25 is used for emails that are not encrypted. So if you and for security you need encrypted mails actually, so for that you should enable TLS, and in that case most of the time the port number would be something like 995 or something. So this protocol has three phases: handshaking, where you perform the authentication, then transfer of messages, and closure. But of course there is not enough authentication in this process, so people can send emails by changing headers so that it appears that the message is received from webmaster@microsoft.com or something. So, and these are most of the time used for phishing. And it's a command response interaction like HTTP and FTP. Commands are in ASCII text and responses are status code and a phrase. So here is an example. In this case, C is for client and S for server. So here the client sends the client sends C lines into its TCP socket, and server sends also the TCP socket. As you can see, you have some commands like hello, mail, or data. So this transcript begins when the TCP connection is established. So 5 commands issued by the client are hello, mail, from, recipient to, and data, and quit. The dot sign from the client indicates the end of the message to server. So this is a carriage return and line feed. The server issues replies to each command like 220, 250, and so on. As you can see, there is a handshake here, and then the data is sent, and the dot denotes that the message ends here. Then the closure happens. So it is really simple, and you can use Telnet to send an email like shown in here. SMTP is a push protocol. The sending mail server pushes the file to the receiving server. TCP connection is initiated by the sending host, but on the contrary, HTTP is a pull protocol. TCP connection is initiated by the receiving host. So let's look at the mail message format. SMTP, the protocol for exchanging email messages. RFC 822 actually defines the headers and so on. This is the standard for text message format. You have the headers to, from, subject, and then the message. But if you're an old user, you know that initially there weren't any attachments that you can put in the body and so on. So people were translating images into ASCII encoding and then submit images in that way. So the receiving person copies that text, passes it, and then turns into a JPEG image or something. So, but today these topics are cleared. Let's say we don't have much problem when we are. People still have some problems when receiving attachments and so on, but not as we had like 20 years ago. So here's an example email. So most of the time in your browser or email client like Outlook Express or something, you see very simple headers, let's say, so you see where the mail comes from, the subject, and who it is sent to. But of course, strange thing here is that, as you can see, there are no Turkish characters here. This is a problem that Middle East Technical University still couldn't solve, because for some reason some people cannot see the Turkish characters. Of course, this is related to encoding, and by simple modification people can do it, but for some reason we couldn't solve this problem. I don't know why, but for all of the years, mails from the President's office always comes in non-Turkish character way. So, and probably 20 years later we will be still talking about this problem. But of course it looks simple here. Your email client shows you this, but originally the headers behind the full mail header is actually something like this. You know, there are a lot of information here. Your client shows you in a simple way. So it is always good to learn how to read and interpret full headers. As a cybersecurity specialist, you should know these headers and what they mean. So SMTP provides delivery storage to receiver server. Therefore, this you have some different mail access protocols to retrieve this information from the server. So SMTP is just for the storage at the server side, but as the client you need a way to retrieve this from the server. And most popular ones are POP, IMAP, and HTTP. POP is the post office protocol. You authorize yourself and download the mails. This is the simple protocol. IMAP is somewhat more complex. This is short for Internet Mail Access Protocol. It has more features, including manipulation of stored messages on the server. But some people, have some problems with this one. We will talk in a minute actually. And you can also do it with HTTP. Many service providers like Gmail, Hotmail allows you to check your email just by HTTP. So you just use your browser, which is for some people more user-friendly. So a lot of people prefer this. So even if they have, for instance, email address at the university, they forward it to their Gmail and just read it from there. It might be a good idea, but you also check if these forwarded messages are sent in an encrypted way. If your email server doesn't support it, probably you are sending all of your private mails to your Gmail account in an unencrypted way. So who listens to the communication can capture your emails. So POP3 characteristics, again I told you this is a very simple protocol. Mails are downloaded to the client host. The user agent issues commands. The server responds to each command, either OK or error in case of misspelling. Below is the sample telnet session. So you log into the mail server with this port. The POP3 server says that it's OK and ready. You input your username. It returns as OK. Then you enter a password and then you successfully log in and so on. And this is a sample POP3 transaction for retrieving 2 messages in the mailbox. But of course, command syntax is specified in a different RFC, and you can check what all of these means. IMAP has further functionalities on the server side. It keeps all messages in place at the server. Each mail is associated with a folder on the server. Inbox is one of the folders. Users can create and delete folders. So actually you can easily see if someone is using POP3 or IMAP, because it's POP3 you only have the inbox folder. Every mail goes there, but at the IMAP you can create different folders, and it synchronizes with your client, actually synchronizes with the server. And once you read an email in the server side, it appears as red. So this way, if you are using different devices to connect your email, making one change in one of them affects all the others. So this way you are synchronized, and it is a desired property actually, because if you are using POP3, once you read an email with your mobile phone, then when you check the same mail at your laptop with an Outlook Express, it will appear as a new email, unread email anyway. So IMAP has a lot of good sides, but you need to, sometimes it is slower because of all of the synchronization and so on. And another thing is that users should know how it works, because I know a lot of professors at the university who chose IMAP when they get your mobile phone. But since all of the emails are downloaded to their mobile phone, it's took a lot of storage in the mobile phone. And in order to overcome this problem, they deleted all of their emails at your phone. But since the changes in the IMAP affects the server too, so they deleted all of their emails they received in the last 30 years at the server. Of course, we brought them back with, from the latest backup, but users should know how this protocol works. Otherwise, you can lose data. But web-based email, as I told you, people prefer this one. It was introduced by Hotmail in 1990s. At the time, maybe you remember, we have like 1 megabyte space or something. But nowadays, with the increase of the storage, since storage become really cheap, we have gigabytes of space at Gmail or other service providers. So you access the remote mailbox via HTTP. But of course, these services like Gmail also supports IMAP and POP3. You don't have to use HTTP to connect to your Gmail account. You can just use POP3 anyway with the software like Outlook Express. So which one is better? Actually, there is no answer to that. POP3 versus IMAP, this is an ongoing debate. But as I told you, for simplicity, sometimes it is better to choose POP3 if you are especially using a few devices, so you don't need much synchronization. But in both of them, a secure communication is needed through TLS, so you have to do the configuration in this way. Otherwise, all of your emails sent in as plain text, and anybody who is listening to the communication can capture your emails. Web-based email is already secure if you are using HTTPS, so you don't have to worry about security there. But of course, the service you are using actually storing all of your emails, so they have direct access to them. So in this case, we are talking about security in terms of the communication. Nobody can listen to the communication and capture your emails, but otherwise you are already storing all of your data on somebody's server. So at that point, we cannot talk about security there, because you are voluntarily giving all of your data to somebody else. And since this is a free service, you cannot expect that they are not doing anything with them. Methods for ensuring authentication is still a hot topic. Email security bottleneck depends on user behavior, because all of your security actually depends on the quality of your password. If you choose a weak password, people can capture your email accounts. Phishing emails are still a problem. Emails with malicious links or attachments are again still a problem. Our filters are really good nowadays, but still a lot of them passes through the filters. So rule of right thumb is never click a link, even if you know that the mail you received is secure and you are expecting it. Instead of clicking it, just write it on your browser by hand. So this was all I wanted to talk about SMTP. Let's move on to DNS and see how it works. So that our general IP addresses are 32-bit, and this is used for addressing datagrams. So internet hosts and routers actually communicate through IP addresses. So, but it is hard to remember IP addresses. General analogy is as follows. Now the phone numbers have a lot of digits, so nobody memorizes the phone numbers of people or friends, so they instead record them on their phone. something with a name that they can easily distinguish. So this way you don't know the phone numbers of anybody, but by knowing their name you can call them. So same is valid for this IP addresses. If you want to visit an IP address of Google, you just type in google.com and you connect it, and the DNS servers actually knows which IP address belongs to Google, so they take you there. But of course, since this is the thing we expect humans to use, but nowadays people even don't use this. For instance, if you want to visit Amazon.com, instead of typing Amazon.com, people type Amazon, so search it on the Google, and then click the first thing that comes up. So at this point you might think that maybe DNS is not necessary at all. People don't remember the web pages anyway. So you can rely on Google and don't use DNS in the first place, but of course this is not a suggestion or correct way of doing it. So anyway, DNS is just mapping between IP addresses and host names. This is implemented as an application layer protocol. Host name servers communicate to resolve names, and this is an address name translation. Further functions of DNS: mail server aliasing using mnemonic names, like for example using mail.metro.edutr instead of kale.general.services.metro.edutr. So another function is web server aliasing and load balancing when multiple IP addresses correspond to one host name. So this is actually important. So I mean, you know that google.com is a single domain name, but probably like 10 different server IP addresses are associated with it. So once you want to connect to Google, your browser checks the DNS server and obtains the IP address. But if you do the same, this time the DNS server will give you the second IP address to balance the load. So this way, even if you visit Google 10 times in a few seconds, probably you will be DNS server giving you a different IP address, so it lowers the balance. So distributed database, DNS are actually distributed database implemented in a hierarchy of many name servers. At the top you have the root DNS servers. At one level below you have DNS servers like for commercial ones, organizations, and educational servers. And in the subcategory you have your university DNS servers and so on. And if you look at the world, there are 13 logical root name servers. These are listed here, but each server replicated many times, so to avoid single point of failure. And here is a picture from 2018, 13 root servers across the globe and their replicates. So as I told at the top, we have TLD, which is top-level domain servers. These are responsible for commercial, organization, networks, edu, aero, jobs, and so on. And you can also have top-level country domains like this. In Turkey we have .tr. Network Solutions maintains servers for commercial TLD, Educo use for edu TLD, and so on. These are some of the top-level domain servers. Authoritative DNS servers are as follows: organizations own DNS servers, providing authoritative host name to IP mappings for organizations named hosts. Local DNS name servers, also known as default name servers, are as follows: does not strictly belong to hierarchy. When a host makes DNS query is sent to its local DNS server. Local DNS server has local cache of recent name to address translation pairs, but the problem is that it may be out of date. So it acts as proxy, forwards query into hierarchy. So this is actually important. I mean, today actually this is fast, but when I had my first web page, maybe more than 20 years ago, I guess, when I updated my name servers, this host actually, so actually when you want to have a web page, first you have the host. You need a host server. You can host by yourself, of course, but you need a static IP for that. Otherwise, you can just pay money monthly or yearly, so that you get some web space, and so that since servers are always connected to internet and have static IP, your web page will be accessible all the time. Then from the same service or from other place, you register your domain name. So you have to map both of them. So for your hosting, for the domain name you bought, you have to put name server of your hosting service. But once you do it, this hosting provider actually reports this change to DNS servers. But sometimes it takes effects in a few minutes. But years ago, sometimes it took more than 1 day. So you update your server, name server, but you try to visit your web page, but it is still inaccessible maybe 1 day later. And this, since these name servers are distributed in the world, when you make the change, maybe somebody in the United States can see the change and visit your web page, but in Turkey it takes maybe a few more hours for you to visit that web page. So these changes sometimes take effect in a long time, and for this reason the caches might be out of date. So it is important for this local DNS servers to check if they are not out of date. So a brief overview of DNS is as follows. So let's say that as a user you are requesting, you wanted to visit the university web page like this. So you have the domain name, but you don't know the IP address. So your DNS query actually send it to the local DNS server, and you ask what is this IP address of this domain name. So if the local DNS server doesn't know it, it asks to a root DNS server, and if they don't have it, they tell you that they don't have it, but suggest you to ask to this TLD domain name server. Your local DNS server asks to, and if they don't have it again, they tell that I don't know it, but you can just check this DNS server. So you ask again, and now since this is the authority DNS server for this domain name, they tell you what the IP address, then you tell it to the user so that the user can visit the web page or use the services from this domain name. But you can also do it in a recursive way if the DNS server supports this. So in this scenario, in this case, if you perform a recursive query, you ask the domain name to your local DNS server, it asks to the root DNS server, it asks to the TLD, it asks to the authoritative DNS server, and the response comes back. So this is somehow preferable because it would be faster, but you know, it's also people might use it to perform denial of service attacks. So at DNS we have resource records, shortened as RR. So this is distributed database storing resource records, and these resources are formatted in this way. So we have 4 values: name, value, type, and TTL. TTL is time to live, determines when a resource should be removed from the cache. And name and value actually depends on the type. So there are a few types. If the type is A, then the name is the host name, value is the IP address. So this is the most common records actually, because this is a mapping from host name to the IP address. But another type is NS, short for name server. So this actually, in this case, name is the domain name and value is the host name of the authoritative name server for this domain. So this way you can track who owns which domain and so on. Type C name is for canonical name, the real name. So in this type, name is the alias name for this canonical name. So for this case, for instance, name is ibm.com, but it's actually serveris.backup2.ibm.com. So value is the canonical name in this case. And finally, for type MX, the value is name of mail server associated with name. So you create your DNS queries in this format. Of course, DNS messages has some format. Both query and reply messages, this format is used. So initially you have 12 bytes for identification, flags, number of questions, and so on. Then you have a variable length of other parts. So at this 12 bytes place, first you have identification, which is 16-bit number for query and reply to query, and you have flags like this. So this is a fixed size, but the remaining part here is actually a variable size. So it is important, and because if the size is really big, then it might be used for denial of service attacks and so on. So these fields are for name, type is for query, RRs in response to query, records for authoritative service, and additional helpful info that may be used are stored here. So how to have DNS security? We don't have time for DNS Sec actually, but maybe we have at the end of the time at the end of the lecture we can talk about it. But it is important and still ongoing research area. But there are many types of attacks, and let's talk about them shortly. So we will talk about cache poisoning, DNS TCP Syn Flood, DNS tunneling, basic NXDOMAIN attack, and denial of service attacks. Let's start with cache poisoning. This is an exploit of a DNS vulnerability where traffic is redirected from a legitimate website to a different one, usually with malicious intent by providing false results to named queries. The attacker forces the target DNS server to make a request for a domain controlled by one of the attacker's name servers. So idea is as follows. Maybe as a student you want to know the IP address of a university domain name. So you send it to ISP resolver. So it asks the root servers, and they don't have it, but say that go ask authoritative servers for university edu, and if ISP asks the authoritative servers, it will get the correct result. But a fake authoritative DNS server storms with malicious IP like this, using various query IDs and source port numbers, so trying to fool this client and saying that this domain name actually belongs to this IP address. And as an additional info, it provides further name servers which are IPs that belong to the fake, for the attacker, and it also claims that I'm also now the authoritative server for .edu. So if you can perform this attack, all of the DNS queries for educational web page will go to this fake authoritative server, and this way you thought that you are visiting a web page you want to visit, but actually you are visiting a fake web page. So there are two ways of doing this. First one is redirect the target domain's name server. The method is as follows. Redirect the name server of attacker's domain to the name server of the target domain. Then assign that name server an IP address specified by the attacker. So DNS server's request is what are the address records for subdomain.attacker.example. So in this case it's type A. And the attacker's response is as follows. Provides the name server. So a vulnerable server will cache the additional A record IP address for ns.target.example, allowing the attacker to resolve queries to the entire target.example domain. Second way is to redirect the name server record to another target domain. The method is as follows. Redirecting the name server of another domain unrelated to the original request to an IP address specified by the attacker. So in this case, the DNS server asks the records for subdomain.attacker.example, and the answer is as follows. Again, a vulnerable server will cache the unrelated authority information for target.example's NS records, allowing the attacker to resolve queries to the entire target.example domain. Second attack type is DNS TCP Syn Flood. In this case, the attacker actually starts a three-way TCP handshake, like the attack we talk about, HTTP. So it starts the handshake. Actually, the attacker starts a lot of normal TCP communication. So it starts the communication. Server actually opens a port for this and sends the egg commands, but attacker doesn't reply back. So in this case, this way you're consuming a lot of resources on the targeted server. So whenever a visitor wants to go to this DNS server and ask for a IP address for a domain, since the server is overwhelmed, they cannot reply back to the legitimate users. Another attack type is DNS tunneling. Actually, this is a very clever and very different attack type than the others. So in this case, think about a scenario like this. So let's say that you're visiting a corporation or a university. So you want to use the Wi-Fi in this corporation or university. So you use your mobile phone or tablet or laptop, but the problem is that you don't have authorization to use it. You don't have, for instance, when you try to connect, they ask you to put in your username and password, but you don't have it. So actually you cannot use the internet. So in this case, can you still use the internet for your purposes? So DNS tunneling is actually an attack like this, where you can use the internet connection even if you don't have the authority. So idea is as follows. You need a domain name for that, of course, and you should be the authoritative DNS server for that. So whenever somebody asks any subdomain name for your domain name, this request will come to you because you are authorized for that. So idea is as follows. When you, again, as I told you, if you are at a university where you don't have the authority to use the internet, they still allow you to perform DNS queries. So in this case, for instance, if you want to visit a web page, just encrypt that web page name, for instance, like this, and ask, send the DNS query where the domain name belongs to you, but here you added an extra information, which is actually maybe the web page you want to visit. So since you are allowed to use DNS, this information is sent to the server that you are using, but your server understands that this message comes from you because there is an encrypted message here. Your server decrypts it and realize that maybe you wanted to visit a web page. So this server actually visits that web page, and for instance, the output HTML can be encrypted again and sent back as an answer as a CNAME response here. So this way you are receiving an again encrypted information, and your device can decrypt it and obtain the information you wanted. So this way you are actually using internet where you are not allowed to use it. So this way you are just using DNS queries. You are actually using the Wi-Fi of the university or corporation where you are not allowed to use the internet. So a client now has two-way transactional communication to a compromised network. The attacker can transfer files out of the network or have complete remote access to the compromised system, and so on. So this is why you have to be careful about DNS queries if you are the IT of the university or the corporation. Another attack type is the basic NXDOMAIN attack. So the method is as follows. Send a flood of queries to a DNS server to resolve a non-existent domain. The cache of this recursive server is filled up with NXDOMAIN results. So you are asking for random domains where the subdomain part is random strings that you generated. So this way you flood a flood of queries are sent for non-existent subdomains for this domain. So this is actually a distributed denial of service attack on the target victim because resources are exhausted on the recursive servers. We also have a distributed reflection denial of service attacks. A combination of reflection and amplification is used. You need third-party open resolvers, so you first employ them. Attacker sends spoof queries to open recursive servers, and now they are amplified and they are reflected back to the target victim. Spoof queries are designed for retrieving large response, so actually you are sending a small amount of data, but now you are requesting large responses, so this actually overwhelms the target. So let's talk more about denial of service attacks and distributed denial of service attacks at the application layer. The goal is to prevent or reduce user access by consuming system resources. The methods are traffic flooding, TCP/IP packet corruption, hanging the system via infinite loop, and so on. Distributed denial of service attacks are the large-scale coordinated attacks, and your primary victims are services under attack. Secondary victims, slave hosts that attack the service. So most of the time you have zombie agents where you're commanding them to, perform the denial of service attacks. So there are sometimes like volumetric attacks, protocol attacks, and application layer attacks. Volumetric attacks are like traffic flooding, amplification. A broadcast IP receives malicious messages. Examples: UDP, ICMP flooding, crafted spoofed IP packet floods, etc. Protocol attacks, like we talk about a few examples where three-way handshake where SYN-ACK and RST attacks. Application layer attacks are some examples are like HTTP flood attacks. So let's talk about HTTP flood attack. The attacker manipulates the HTTP and POST requests in order to attack a web server or application. The method: a web browser sends GET or POST request to a server. GET flood is as follows. The GET request is used to retrieve static content like images. Typically, this induces relatively low load on the server per request. Actually, this is important because if you have a web page where the data is static, then there is no need for you to use like databases and for every visitor perform the same approach and go to a database and generate the requested data. If the data is static, don't bother with it. Convert it into HTML file, and this way it is very hard for them to perform denial of service attacks. But this is why post flood is more effective, because post requests are more likely to require the server to perform some kind of processing, such as looking up items in a database. Therefore, HTTP post flood attacks typically impose higher load on the server per request. This is actually what happens when you are trying to register for a course at the beginning of each semester, because everybody is trying to log in the registration page, and in that case there are many database connections, like checking your username, retrieving your data from the database, and showing you the available courses and so on. But of course this is an implementation error. As I told you before, a few thousand students shouldn't be able to overwhelm such a system. So this means that the database lookups and so on are performed in a very bad way, that students involuntarily performing a denial of service attack. Methods of mitigations are as follows. HTTP flood attacks use standard URL requests. It is quite challenging to differentiate from valid traffic. The solution is use the combination of traffic profiling methods that includes identification of IP reputation, tracking abnormal actions, employing progressive challenges. HTTP flood attacks are difficult to overcome. An example is Slowloris. So what is Slowloris? A DOS attack tool that allows a single machine to take down another machine's web server with minimal bandwidth and side effects on unrelated services and ports. Slowloris tries to keep many connections to the target web server open and hold them open as long as possible. It opens connections to the target web server and sends a partial request. Periodically, it sends subsequent HTTP headers, adding to but never completing the request. So you are slowly sending a small amount of data like HTTP headers. So Server doesn't kick you out because your connection is not timed out, because you're slowly sending data, keep sending them, but you're never finishing the request. Affected servers will keep these connections open, filling their maximum concurrent connection pool, eventually denying additional connections attempts from clients. So this is an example where you can perform a denial of service attacks without needing many zombies. You can just do it with a single PC. Mitigation is as follows: no reliable configuration of the affected web servers that will prevent the Slowloris attack. Ways to reduce the impact of such an attack is increase the maximum number of clients the server will allow, limit the number of connections a single IP address is allowed to make, impose restrictions on the minimum transfer speed a connection is allowed to have, and restrict the length of a time a client is allowed to stay connected. So this is actually requires a good configuration of your server. An example approach by Insula. So application layers, so layer 7 distributed denial of service attacks are much more complex than lower layer attacks. So they have something called 5-ring approach to distributed denial of service protection. So they have need dedicated security team, behavior anomaly, progressive challenges, web application firewall, visitor reputation, and client classification. An example is, in this case, for the client classification is as follows. The goal is to distinguish between human traffic and bot traffic and flag block malicious volumetric traffic. And visitors, whitelisting and reputation, classify the remaining traffic into gray and white visitors. Here's an example for that where an IP is blocked. And for the other protections, web application firewall for direct attack vectors, and progressive challenges, for instance, session cookies and CAPTCHA, or behavior anomaly detection, recently rule-based algorithms. But it depends on how good your rules are, and you have to keep updating them depending on the attacker's behavior. So this is the end of our talk for the layer 7, application layer security.